Okay, welcome to this tutorial, guys, on mechanical vibrations. We are going into system responses. In the previous video, we went through how to get the equations of motion and we did a number of examples, and we went over two methods, namely Newton's method and the conservation of energy method. Okay, so what is the system response? So that is what we're going over in this video. Cool stuff. Okay, before we do that, there's some terminology or some things that we need to define. Okay, and we're going to start with our natural frequency. Okay, so our natural frequency is the frequency at which an undamped system will vibrate with no forces. Okay, so it's defined as omega n, and it's equal to the square root of your k equivalent over your m equivalent. Okay, that's also equal to, if we have, so this is for a translating body, and if we have a rotating body, it can be equal to our kt equivalent of our I equivalent. Okay, yeah, okay, after that we need to understand that some systems, the examples we did previously, had no damping, if I'm correct. Yeah, I don't think there was no damping, but in these examples that we're going to do today, there's damping, so we need to introduce a symbol for damping. So we have the damping ratio, okay, and it's this weird symbol C, okay. That's how I draw mine, at least, okay, and it is equal to, or it is defined as equaling our damping constant over 2m omega n, or the one that I most frequently use is C over 2 square root of m equivalent k equivalent. Okay, so that's the one I use. And then lastly, we have our damped ratio, or damping frequency. Okay, and this is given the units. Okay, so let's say it's given the symbol omega d, and it is equal to omega n square root of 1 minus c squared. Okay, and given these units, these are in radians per second. This is unitless, and this is in radians per second once again. Okay, so something that's important to know about our damping ratio. So our damping ratio, we can say it defines the system response. Okay, so the system response just tells you how the system will actually respond to the vibrations. It's usually defined in terms of displacements or in terms of angle theta in radians. But yeah, so it can be defined either as a distance in x or a angle theta. Okay, so let's see. There are three main situations, or rather four even. So we can have undamped. Okay, that means that C is equal to 0. We can have under damped, which means that C is less than 1. We can have critically damped, where C is equal to 1, and we can have over damped, where we have C is greater than 1. Okay, typically the kinds of questions we're going to get is those three, because overdamped is the response of overdamped is in cosh and sinh or sin h, and therefore we will probably be focusing on undamped, underdamped, and critically damped. Okay, so looking at the underdamped case, let's see, the system response can be defined as x of t is equal to x naught cos omega n t plus x dot naught over omega n sine omega nt. Okay, I'm not going over the derivations of these. I'm just giving you the equations of them, and I'll be showing you how that we use them. Okay, so what is this? This is our initial displacement, and x naught dot is our initial velocity. Okay, then we are moving on to underdamped. Okay, for underdamped, we have the situation x of t is equal to e to the minus c omega nt times x naught cos omega dt plus x dot naught plus c omega n x naught over omega d sine omega dt. Okay, that's a nice equation. You will get these equations as part of your formula sheet, or you can probably write one up. Okay, but you will start remembering them as well once you use them extensively. And then finally, for critically damped, we have x of t is equal to e to the minus omega nt times y x naught plus x dot naught plus x naught omega nt. Okay, so those are the three system responses. And this, so those are system responses. And so maybe a nice thing would be to write all of these equations down, or if you have it as a formula sheet, then this would be quite important. Okay, so once we've done that, I think we can actually get into an example of two, just to show you. Okay, so let us start with example. Let's start with a fairly simple example. Okay. Okay, so the example looks something like this. We have a rod like that, it pivots about the point O. Okay, we've got a spring attached, value of K, and we have a damping C. Okay, this distance is L over 2, this distance is L over 2, and the way that the system rotates is like this. So we have a rotation like that. Okay, so an important thing to understand is, I mentioned it in the previous video, but we have to use Newton's method in this question. And the reason why we have to use Newton's method is because of that damper. Okay, if there is damping, then we cannot use the conservation of energy method. Okay, so always with these kinds of questions, the first thing we ever have to do is to start by drawing ourselves a free body diagram and getting the equation of motion. So let's start with our free body diagram. Okay, so I'm going to draw it after it's been displaced. That angle there is theta. This right here, the force is KL theta. This force is acting upwards as well, which is C L over 2 theta. Okay, we have a mass here, mg. Now the question is, do we ignore this or do we take this mass into consideration? So is it in static equilibrium or is it not? Okay, so how we figure this out is, if we cut this spring, what's going to happen to the system? If we cut that spring, the system will definitely rotate and move downwards. Okay, so it is balanced by the spring's displacement, and so we can say that we can ignore this mass in our moments. Okay, again we have our reaction forces Oy and Ox. Okay, so once we've done that, let's just see, we've got our all our important things. We can put in some lengths over here, L over 2, L over 2. Okay, and then we can start doing our summation of our moments about point O is equal to IO theta double dot. And which way is theta rotating? That way. So we have it going that way and that way. Okay, so taking the moments, let's start. We have minus, let's start with the spring, minus k, and then the moment arm from here all the way to there is L, so that's going to be k L squared theta minus c. The moment arm is going to be L over 2, so we're going to square that, theta. We're going to ignore this mass, is equal to IO, okay? So the moment of inertia for, or the mass moment of inertia for a uniform slender rod rotating about a point is 1 over 3 ml squared theta double dot. Okay, taking the left hand side of the equation across to the right hand side, we end up with 1 over 3 ml squared theta double dot plus kl squared theta plus, I'm going to write this as 1 over 4 cl squared, that's a theta dot, my bad, theta dot, yeah, theta dot is equal to 0. Okay, now we can just run some checks like we normally do. Just going to run them right over. These are both positive, positive, positive. So we're happy with that. If we're looking at the units, we have kilograms meters squared per second squared times our radians. No one really cares about radians, so I'm going to leave them out actually. And we have Newton meters. Over here we have newtons per meter times meter squared, and we're left with our Newton meter. Here we've got Newton second per meter times meter squared and radians per second. Leaving out the radians because I don't care about them. We can cancel these, and we have Newton meters. So all our units are correct. Cool stuff. Okay, now I'm going to give you some values for these things. Okay, so let's say the question says that L is equal to 1 meter, M is equal to 30 kilograms, K is equal to 250 newtons per meter. Then we can also say that we've been given the damping ratio, C is equal to 0. Let's say 0.2, and our initial conditions, theta dot naught is equal to 0.3 radians per second, and theta naught is equal to 0. Okay, so knowing all this information, we can rewrite this as follows. So we have 10, substituting values in, theta double dot plus 250 theta plus, I'm going to leave C as it is because that we've been given the damping ratio. Okay, everything looks good. Okay, so once we know this, some important things that we need to do. So once we've got this, we want to figure out, so this is our equation of motion. Okay, and from this we want to get the system response. Okay, so what is the system response? Okay, firstly we've been given that C is less than 1, and so we already know that this is an underdamped system. So from knowing this, we can already get a baseline for what our equation of motion actually looks like. It's going to look like this: x of t is equal to e to the minus c omega nt x naught. Okay, let's actually, because we're working in theta, let's say theta is theta naught cos omega dt plus theta dot naught plus c omega n theta dot, theta naught rather, over omega d sine omega dt. Okay, cool stuff. So this is the basic format of our system response, and from the get-go we know that theta naught equals 0, so that term goes away completely, and we have that term go away completely as well. Cool stuff. That makes our life a little bit easier. Okay, so what do we have and what do we need? So we have C, got the value of C, we need omega n, okay, and we need omega d. So let's start with omega n is equal to the square root of k, which is 250 over 10, and this gives us a value of 5 radians per second. Okay, we know the value of c is equal to 0.2, and so we can get omega d equals omega n squared square root of 1 minus c squared, and that's going to be equal to something wrong. Give me one. It looks like, there we go, it's not omega n squared but rather omega, and we have a value of 4,89898 radians per second. Okay, so I'm going to leave it there. Okay, once you've got that, we can say that we have everything that we need. Yep. So I'm going to say that theta, or the system response, is equal to E. So we have C, which is 0.2 times 5, which is equal to 1, so minus T. Okay, that term falls away. So then we have theta dot naught, which is 0.3 over 4.89898, which gives us a value of 0.06124 sine, and then our value of omega d is 4,89898 t, and that is our system response. Great stuff. Okay, so an important thing to know, and a question that they always ask, is what is theta max? Okay, so this term right here, what does this term actually do? It is killing your amplitude. Okay, so what does that mean? It means that this term, as t increases, the amplitude will always decrease. Okay, so the amplitude always decreases. So what we need to do is, we can't simply say that the maximum value is that value right there. We can't say that. We have to carry out the second derivative. Okay, so let's do that. So carrying out the second derivative, I'm going to base it straight off there. So I'm going to write theta as a function of t is equal to e to the minus c omega n theta dot naught over omega d sine omega dt. Okay, then theta dot of t is equal to, differentiate the first function, minus c omega n e to minus c omega n t omega n t theta dot naught over omega d sine omega dt. Okay, plus first term, we leave that, and differentiate the second term. Okay, derivative of sine is cos, but we're going to get us omega d cos omega dt. Okay, then what I'm going to do is make this equal to 0. When I make this equal to 0, I can take this to the other side. So we can rewrite this, or I can do the changes in red. I'm going to make this positive as I take it to the other side, and the equal sign is going to be there. Okay, so then what we're left with, these terms cancel, these terms cancel. Okay, omega d is still left, sine omega, that's still left, and this term right there is still left. So then what I do is, I'm going to take this cos omega dt across, so then I'm left with tan omega dt. So that takes care of those two values. We've got an omega d, and we've got a c omega n. Then what I'm going to say is t is equal to tan to the minus 1 omega d c omega n over omega d. Okay, and there we can figure out our time value. So putting values to this, remembering that everything must be done in radians, we can have tan to the minus 1 is equal to omega d is, let's get the value, 4.89898 over 0.2 times 5 all over 89898. Okay, let's put that into our calculator, and what we get is a value of t is equal to 0.27954 seconds. Okay, so now we know the time. So with this time, we can plug our value of t into here and here, and we can get our theta t max. Okay, so this here was our system response quite nicely, and theta max is going to be equal to, let's plug in the answer. Okay, okay, and we're left with an answer of 0.04537 radians. Okay, so that is our theta max. Okay, so I think this video is getting quite long already, so I will leave the next example, or maybe I should write out the next example and leave it for you guys to try, and then I'll go through it in the next video. So let's do that. Okay, so the next example looks something like this. We have a nice wall. Okay, then we've got a disk. There is no slipping. This is the point P. Okay, we've got that distance R, and we've got a damper connected to the wall, and we have a spring connected right there. Here we have value K, here value C. Okay, this distance here is A. Okay, and we have that as being X coordinate, and that as being our theta coordinate system. Okay, am I missing anything? We can say that this has a mass of M. Okay, and that's the point O, that's the point P, everything looks good. So let's say we want the equation of motion. Okay, once we have the equation of motion, we want to use the following equation. So equation of motion question mark, and then let's give it some values. Let's say the M mass is equal to 5, R is equal to 0.25, A is equal to 0.1, K is equal to 500, C is equal to 15, and X dot naught is equal to 0.4, and X naught is equal to 0. Okay, and last we want the system response. Okay, cool. Thanks for watching, guys. Hope you find this question quite easy. If you don't, I'll go through it in the next video, and hopefully it will be easy after that. Okay, thanks for watching.